Mechanisms in motion are short revision videos which show you the effect of arrows in organic chemistry mechanisms. As the format is a quiz, you will be presented with multiple options for how the mechanisms will occur. Based on your choice, move ahead to the timestamp and you will see how your choice affects the reaction. If you are correct, you will move on to the next step in the mechanism. If you choose the incorrect or less likely answer, the reason for this will be explained and then you'll be given the correct answer. At the end of the video, you will see the full drawn-out mechanism showing the curly arrows moving the bonds. The Grignard reaction is a method to form carbon-carbon bonds. The Grignard reagent is a carbon-containing group which is bound to a magnesium bromide. The bond between magnesium and the carbon stabilizes the negative charge on the carbon group. The negatively charged carbon group is now capable of attacking at electrophilic positions in other molecules in solution. The first step when doing a Grignard reaction is to understand what conditions will allow for a successful reaction. As Grignard reagents are not stable on their own or in certain conditions, the choice of solvent is important to ensure you obtain the product you desire. For this reaction, should the solvent be ethanol, diethyl ether, or hexane? By using ethanol, you are adding a polar protic solvent to solution. The proton on the hydroxy group is very acidic, meaning it can easily be attacked by the negatively charged ethyl group of the Grignard reagent, forming ethane. This has deactivated the Grignard reagent, preventing the reaction you wish to occur. Therefore, this is not the correct step. By using hexane, you are using a nonpolar aprotic solvent to solution. While there is no acidic groups to deactivate the Grignard reagent, the hexane is not a suitable solvent for this reaction. This is due to the instability of the Grignard reagent, which means for the reaction to work, you need to have a solvent which will help stabilize the reagent. Diethyl ether is a nonpolar aprotic solvent which is able to coordinate the magnesium of the Grignard reagent through the oxygen lone pairs. Similarly, there are not acidic groups which would be able to deactivate the Grignard reagent. This means the Grignard reagent will be stable enough in solution to undergo the desired reaction. The first step of the Grignard reaction is the attack with the carbon of the Grignard. This can either occur as the nucleophilic attack at the ketone, or deprotonation at the alpha carbon to form the enolate. With enolate formation, the alpha carbon is deprotonated, forming a double bond which results in breaking of the carbonyl bond, ending with a negative charge on the oxygen. This does not occur as the Grignard reagent is not basic enough to remove the alpha hydrogen. Therefore, this is not the correct first step. The nucleophilic attack at the ketone results in carbon-carbon bond formation. This is the correct next step. Once the tetrahedral intermediate is formed, the oxygen anion is protonated by addition of acid to solution. In adding the acid, you will also be quenching the remaining Grignard reagent. This slide shows the final product for this reaction. What would happen now if the ketone above was replaced with the equivalent carboxylic acid? Would there be no addition by the Grignard, the addition of one ethyl group, or the addition of two ethyl groups? As above with the ethanol, the carboxylic acid unit contains an acidic proton. This hydrogen would protonate the Grignard reagent, preventing the desired reaction from occurring. This slide shows the final product for this reaction. What would occur if the hydroxy group was replaced with a methyl group to form an ester? Would there be no addition by the Grignard, the addition of one ethyl group, or the addition of two ethyl groups? The change to an ester would allow for two separate additions of ethyl groups. This occurs because when the first ethyl group attacks a carbonyl, a tetrahedral intermediate is formed, which is bound to a methoxy group. The methoxy groups are good leaving groups, meaning the carbonyl can be reformed by kicking out the methoxy group. This leaves you with a molecule that functionally acts the same as the first molecule in the video. The ketone of this molecule can then undergo another addition, after which protonation will occur, resulting in the alcohol product. This slide shows the final product for this reaction. This slide shows the functional group tolerance of Grignard reagents. With carboxylic acid, no additions occur. With aldehydes and ketones, only one addition occurs, and with esters, two additions occur. This slide shows the curly arrow mechanism for this reaction. Thanks for watching the video. If you found it helpful, please leave us a like or a comment, and subscribe if you'd like to see future videos of mechanisms in motion.